All right, so our first speaker for the afternoon lightning talk session is Zi-Wen Liu from Perimeter Institute. Please go ahead.
Okay, thank you. Thanks to the organizers for putting together this conference. I'll use the next few minutes to quickly introduce two works. The first one is about no-go theorems for quantum resource purification based on these two papers, joined with Kunfang from Waterloo. This work concerns two important issues in practical quantum information processing. The first one is that quantum systems are inherently very susceptible to noise and errors. So the general procedures for purifying noisy quantum systems are crucial in reality. And the second one is that practical setups usually entail various kinds of limitations on the accessible resources or easily implementable manipulations, which underlie the resource theory language. So in this work, we're going to show that there exists universal limits to the accuracy and efficiency of purifying generic noisy quantum resources. More concretely, the tasks we consider are of the following forms. In the state setting, we wish to approximately transform certain noisy or mixed states to a pure target resource state by free operations. And analogously, in the channel or dynamical setting, we consider unitary resource channels as the target and free supermap as the transformation. Note that a key complication that the channel setting has is that multiple instances can be used in presumably inequivalent ways, like in parallel or adaptively. Here are the results. We derive lower bounds on the error of any such purification task, which imply universal no purification rules when you wish to transform generic noisy states or channels to any pure resource state or channel by any free operation or supermap in virtually any resource theory with a well-defined free set. In particular, as illustrated on the left, we could obtain such trade-off bounds between the accuracy and success probability of the purification protocols, which are akin to uncertainty relations. An important implication is the logarithmic lower bound on the scaling of total overhead of distillation, which is a key type of figure of merit. We developed two different types of approaches that induce such no purification bounds. One is based on analyzing the hypothesis testing relative entropy monotones. And the idea behind the second one is to extract the free part and of the input and track its behaviors. In the papers, we discussed these fundamental limits in relation to a broad range of important practical and physical problems, which include the cost of magic state distillation, which is the key subtheme that underpins the leading scheme of fault-tolerant quantum computing, and constraint, in particular covariant quantum error correction, which we have already heard about for a few times on Tuesday, and quantum channel theory, and noisy circuit synthesis. Actually, more applications are expected, and please check the papers for details of these discussions. So should I pause here a little bit?
Thanks for the talk. If there's a quick question for Zi-Wen, I think we could accommodate that.
Sorry, can I see that somewhere?
There's nothing in the chat right now, as
Okay.
far as I can see. I was just asking anyone if they wanted to unmute and ask a quick question. But we should probably switch now to your other talk.
Okay, great. The second one is about manual quantum magic. This is a joint work with Andres Winter. First, a little bit of background. As we all know, magic or non-stabilizer state are an important, indispensable type of resource that empowers quantum computation. Therefore, a understanding of magic at the quantitative level is crucial to the study of many important topics like quantum complexity and classical simulation costs and so However, our previous understanding of magic at the quantitative level are largely about small individual systems, or rely on the discrete Wigner function, and which only work well for special dimensions. In this work, we want to start the exploration of magic in generically highly entangled many-qubit systems. We find that the theory is mathematically very interesting, and we also explore the physical meanings and relevance of many-body magic. Okay, first we want to address how to operationally quantify many-body magic and the important mathematical features of these measures. The key messages of our results are summarized as follows. First, we give some arguments for that the mean relative entropy to the stabilizer states d-min and the free log robustness of magic LR are in some sense the extreme magic measures that we care about the most. And then we actually show that the free log robustness is actually upper bounded by approximately n. And on the other hand, the d-min is lower bounded also by approximately n, with overwhelming probability for a hard random state. That is actually all these good many-body magic measures are highly concentrated around n. A implication that might be particularly relevant to this audience is that these one-shot reasonings actually lead to an improved understanding of the asymptotic reversibility of magic transformations in the asymptotic IID limit. Still, the calculation of magic for explicit states is a very difficult problem. Here we give a recipe for the class of hypergraph states, which can already host rich entanglement structures by relating their magic to explicit Boolean function problems. Then we go on to consider the practical and physical relevance of many-body magic. First, let's consider the model of measurement-based quantum computing where we do Pauli measurements online. This model is practically motivated and make magic the critical feature of the many-body initial state. Now we can actually show that here too much magic also destroys the power of quantum computers in some sense, which is analogous to the situation of entanglement. And here magic is actually an even more clear-cut resource for quantum computation. So this actually may raise further curiosity into how to characterize the origin of quantum advantages. Finally, we put forward some condensed matter physics perspectives. Notably, in this companion work, we showed that magic is actually a necessary feature in a large class of the so-called SPT phases in 2 spatial dimensions and beyond. Note that the usage of SPT states in MBQC is widely studied, and certain representative SPT states are known to have hypergraph state structure. So in the paper, we demonstrate the application of the Boolean function coding theory techniques to derive bounds for certain models of SPT states. And we also give some discussions about the connections between many-body magic and the computational aspects of quantum phases matter, which is an exciting forefront of condensed matter physics. Again, if you're interested in the details, you can check the archive paper, and thanks for your attention.
All right, thank you, Zi-Wen. We should probably transition to the next speaker.
Okay.
And reserve longer discussions and questions for Slack. The next speaker is Levin. Thank you for being ready. Do you want to screen share? Hi.
Okay. All right.
We'll wait a little bit.
Sure.
Time. We're a bit too lightning. All right, our next speaker is Joshua Levin, coming from CU Boulder. Please take it away.
Hi, everyone. So this is joint work with Oliver DeWolf and Graham Smith, University of Colorado Boulder. And since this is Beyond IID, I'm going to focus a little more on the correlation measures and a little less on the holography. But the goal here is to understand the types of correlations that can exist between the parties of a multi-party mixed state. So for pure states, essentially entanglement entropies and linear combinations thereof tell you everything you might want to know about the correlations that exist between the parties. But to understand the correlations between the parties of a mixed state, we need to look beyond linear combinations of entanglement entropies. And so we're led to these objects called optimized correlation measures. And first, let me just define an n-partite correlation measure as just a real function of n-partite states, which is monotonically decreasing under local processing on all parties. And the monotonicity requirement is desirable because correlation shouldn't be something that we can make more of with local operations. So the typical example, at least for n equals 2, would be something like the mutual information. And from there, we can define an n-partite optimized correlation measure as simply an n-partite correlation measure of this particular form, where it is an infimum over all possible n-partite purifications of the n-partite state. And what you're minimizing is a particular linear combination of entanglement entropies of the purification. So here both indices I run from 1 to n, so there are 2n total parties here. And that's why the total number of possible entanglement entropies appearing in the linear combination is 2 to the 2n minus 1. It's just the possible subsystems of the purification. And so some typical examples of these include the entanglement of purification. So these are both examples for n equals 2. So we have this bipartite purifying system represented by these lowercase letters. And then for entanglement of purification, we're minimizing the entropy of big A, little a. And then another familiar one would be the squashed entanglement, where we're minimizing this particular conditional mutual information. And so this work, we focus mostly on tripartite optimized correlation measures, although we do talk a little bit about general n-partite optimized correlation measures, but I'll just talk about the tripartite ones. And so essentially we construct a list of tripartite optimized correlation measures. And the way that we construct them is as follows. First, we impose symmetry on the linear combinations of entropy that are allowed. This is to simplify the analysis. And basically, we only allow objective functions that are built out of linear combinations of these symmetrized entropy functions. And so once we impose symmetry, we then impose monotonicity to make it a correlation measure. And the way we do that is we construct only linear combinations of these above symmetrized objects that satisfy one of these two conditions. Either each term either contains both big A and little a, or neither. Or if a term contains only big A and some other systems, then there must be another term with the opposite sign containing little a and some other systems, such that these other systems X and Y are disjoint. And so we're able to show that if every term, or if all the terms in our linear combination satisfy these constraints, then we will have monotonicity not only on the party A, but the parties B and C as well, due to the fact that we've already imposed symmetry. And then finally, we need the infimum to exist. So we don't want to be able to make the objective function arbitrarily large and negative by choosing the right purifications. And so the way we do that is we consider the objective function, but in the limit where the parties are trivial. So uppercase A, B, and C are 0. And so f, the objective function, with 0 for the parties and only forming pure states out of the ancilla, just looks like some linear combination of entropies of the individual ancillas. And then we require that this coefficient is non-negative. And then we were able to show that if you impose this condition, then all the infima will exist, and your correlation measure will be well defined. And so just using these three, imposing these three conditions, we end up with a list of 13 tripartite optimized correlation measures. Here they are.
Josh, we have to stop now. I'm sorry.
Okay. So
You're welcome to record an extended talk and post it and send it to me. We can post it online.
Okay, sure.
The next speaker could share the screen. Sorry about that.
No, that's okay. That was basically the point, just a list of correlation measures.
Okay. Thanks, Ian. Please go ahead.
Okay, can you hear me?
Yes.
Okay, yeah. Hi, I'm Ian. I'm going to talk about joint work with Zi-Wen and Norbert Luckenhaus on numerical finite size QKD. So the motivation's pretty straightforward. We want to implement QKD in real life, which means we have finite resources, and also that there will be imperfect devices. This leads to a problem because if you want to analytically determine a tight finite key rate, you normally need some sort of symmetries of your protocol. So our solution is a numerical method that doesn't need these symmetries. It uses Renner's framework for finite size effects, and it extends the numerical method for asymptotic key rate to the finite regime. So the results are that we improve the analysis of parameter estimation, we develop a general numeric method for tight finite key rates, and we investigate these tools for different protocols. So the improved parameter estimation, the basic idea is you want to construct a set that you're going to optimize over that ignores states which your protocol would normally abort on. The problem is that the way one normally constructs this set functions as a function of the dimension. So it looks like if Alice and Bob throw out information, they're more secure against Eve. So we prove that's not true by showing that you consider multiple forms of data processing at once and retain the same security parameter. Using that, we develop our general numeric method. It's based on the asymptotic one, which the basic idea is that you have a minimization problem over a set of states, and you're minimizing the conditional von Neumann entropy. And the idea numerically is that you start with some attack by Eve, you try and converge to this rho star, which would be the optimal attack by Eve. You linearize at the point rho, which is where your numeric stops, you take the dual, and therefore by going to the boundary, you always have a lower bound on the optimal attack. And in the case where rho equals rho star, you'll have a tight result. So in the finite key case, basically we're just increasing the set that we optimize over. And so we prove that this is still a semi-definite program, and we prove that it has tightness and reliability like before. And moreover, we show that it has the ability to consider both collective and coherent attacks. So just as a quick example, you could imagine that you have reference, you're doing BB84, but when Alice sends her BB84 states to Bob, they get rotated by some unitary. So it's as if Bob's been given the wrong reference frame. Now, with enough parameter estimation, you could actually undo this, but if you just check the phase error and the bit error, you wouldn't actually be able to detect this rotation. And so this is a problem because there's a scaling between the finite size effects and the fine-grained statistics, which you can see here because the fine-grained statistics asymptotically get a better key rate, but in the low number of signals, because you do data processing, the phase error does better. But using our numerics, you can consider both at the same time, and then you get a better key rate in all regimes. So to summarize, we improve the analysis of the parameter estimation subprotocol. We construct a general numerical framework for evaluating finite key rate of QKD protocols in finite dimensional Hilbert spaces. And we consider when these tools are useful. And one place where they might be useful that we didn't look was investigating side channels. Thank you.
Thanks a lot, Ian. We have to keep moving. Sorry.
No problem.
So, longer discussions on Slack. I sent a reminder for all speakers to send their slides to Beyond IID 2020 at Gmail. Next up is Michael Nathanson. If you could share your screen. Thank you. Just wait a little bit.
Yeah.
Okay. Our next speaker is Michael Nathanson from St. Mary's College. Please tell us about your research.
Excellent. Thanks for giving me the opportunity. I'm going to be talking about entanglement as a resource for LOCC discrimination. And this is joint work with Bandyopadhyay and Halder. And so this is the standard LOCC setup where you have a multipartite finite dimensional system. Each system is controlled by one party. But what I want to imagine is that an adversary encodes an alphabet as an orthonormal basis, and Alice and her collaborators will try to recover the identity of the matrix using, or the message, excuse me, using only local operations and classical communication. So I call this data seeking, right? Because it's data hiding from the perspective of the people who are trying to recover the information. For today, we're going to focus on the problem of unambiguous state discrimination, which just means that you can recover each of the possible messages, or else you'll get an error message, okay? And so the technicals will be in my longer talk. But the key thing is that LOCC state discrimination is challenging. Only product bases can be unambiguously distinguished with LOCC. But if we have a resource state, the shared entanglement, then it's possible for them to do more, as we see in the example of quantum teleportation. So this is not anything that people don't know already, but it's the notion that we have a resource because it enables an information task, and it also gets consumed in the process. Okay, so we have this bipartite maximally entangled state as sort of our picture of what that looks like, or our model. So in general, the adversary presumably knows which entangled resource state they're going to start with, and will choose their basis B accordingly. And so what we're looking for is an entangled state that will allow our local agents to distinguish the elements of any orthogonal basis of H, regardless of which one the adversary chooses. And if so, we're going to call it a universal resource. Okay? And the way that we understand this is this nice equivalence that says that phi is a universal resource, is a resource to distinguish the elements of a basis B. If it's possible to transform phi, or phi its conjugate, into each of the elements of B. So it gives a way to relate the problem of LOCC state discrimination to the problem of state transformation, which is the way that we usually talk about entanglement. So this is really useful. And it's a nice equivalence. And so what this means is that if we're in a system like a 3-qubit system where there are multiple classes of maximally entangled states that cannot be transformed into each other, then it means that no universal resource exists within the space itself. So there is no 3-qubit universal resource. The only way that you can get a universal resource for a 3-qubit system is if you up the dimension. And so there actually is one for that includes 2 qubits and 1 qubit. So if you increase the dimension, this allows you to do that. And you have this picture of the partially ordered set that comes out of entanglement transformations. And this is for 3 qubits, and in general, that's this sort of behavior persists whenever there's multiple classes of maximally entangled states. So there's lots of cool material on this, and there's more details will be in my extended talk and on our 2 papers on the archive about this. So thank you very much. Appreciate it.
Thanks a lot. All right, so I think we have to keep moving. The next speaker is Felix Leditzky. You go ahead and share your screen. I think
Michael needs to stop sharing first. Okay,
yeah.
Cool. Thanks.
All right, I think we just wait a few seconds.
Sure.
All right, so our next speaker is Felix Leditzky from IQC and Perimeter. Please tell us about your research.
Thanks, Mark. So I want to present my paper, Error Thresholds for Arbitrary Pollen Noise, that I wrote together with Johannes Bausch. And we discussed the quantum capacity of a quantum channel, which captures the ability to generate entanglement using a quantum channel. So my favorite way of thinking about this is that we have Alice and Bob separated in separate labs, but they're connected by this quantum channel. Alice prepares some pure multipartite state, sends part of it through the channel. And then Alice and Bob share some giant mixed multipartite state. And then they try to distill entanglement from that, to distill EPR pairs. And the work of Devitak and Winter tells us that they can do that at the rate of the coherent information of this multipartite state that they share, which is given here. But it's a problem to find out the optimal rate of doing this because of a phenomenon called superadditivity of coherent information, where there are certain channels and certain input states psi, such that this multilateral coherent information here is strictly larger than the coherent information that you get using just one copy of the channel. The quantum capacity as the optimal rate of distilling EPR pairs is then given by the maximum over all of these multilateral coherent informations. And this is captured in the capacity coding theorem that I've written down here. The problem with this is twofold. So first of all, this is an unbounded optimization problem because of this superadditivity. And furthermore, we have some very pathological behavior for this coherent information sitting in here. And even when you fix the n and kind of just try to solve this optimization problem for a fixed number of channel copies, in the interesting cases, this will be a non-concave maximization problem. So computationally speaking, this is also a problem. We tried to attack this in our paper by focusing on a certain class of channels called polychannels. So these are channels where with a certain probability, you have one of the poly errors XYZ happening on your qubit. And in order to test the coherent information or to kind of get lower bounds on the quantum capacity, we choose graph states, which are a certain example of stabilizer states defined in terms of a graph. So I've written down a graph state here, where for each vertex you have a certain stabilizer, and then the graph state is the unique state stabilized by all of these stabilizers. And the nice thing about these graph states is that if you have a poly channel acting on it, then the different poly errors are translated into Z-type errors in a very nice way. I'm not going to explain this in detail, but here you can see graphically how this works, and I'll explain it in more detail in the extended talk. And so we can use these specialty coherence properties to compute the action of a polychannel on the graph state. And what's nice is that we can also leverage the symmetries that we have in the graph, which are given by graph automorphisms, in order to speed up the algorithm, which is in the beginning exponential, but using these symmetries, we can speed this up and actually compute coherent informations for like large block lengths. And we do this in the paper. The cool thing is that we obtain analytical expressions for the coherent information and given in terms of the poly channel probabilities. And then we can go and evaluate for arbitrary poly channels in this polychannel simplex, this coherent information, and try to compute error thresholds. And we do this in the paper. We can produce these nice looking plots, which are so-called threshold surfaces. And the blue and green regions here are where we have superadditivity of coherent information. And we're able to test these certain families of graph state codes, for example, repetition codes, or these novel tree graph codes here. So I hope I got you hooked. Please check out the extended talk. Thanks.
Thank you, Felix. Yeah, so if there are any questions, maybe go to the Slack. As you know, our final speaker for today for the lightning talk session, Esmaeil Karimi. Please share your screen. And I think it's fine if you just go ahead and start.
Hello, thank you for giving me the opportunity. My name is Esmaeil Karimi from Texas A&M University. Today, I'm going to talk about our work, entangled photon detectors with memory. This is a joint work with Mina Sholyanin from Rutgers University and Philip Whiting from Macquarie University. In quantum key distribution systems, there are two remote parties commonly referred to as Alice and Bob who seek to establish a secret key by communicating over a quantum channel and a public channel. There's a third party, Eve, who eavesdrops on this communication. A time-entangled photon source emits entangled photon pairs when it's sent to Alice and the other to Bob, and the time axis is divided into bins such that a photon arrives in each bin with probability P. Upon detecting a photon, detectors go into a recovery period. We assume that the length of a recovery time per detector is D bins. Alice and Bob timestamp their photon arrivals, and then they map these timestamps to bit strings. We define the raw key rate of a scheme as the expected number of raw key bits that can be generated per bin. The sequence of photon arrivals forms a D+1 state Markov chain, as you can see in this slide. And we show that the maximum number of raw key bits per bin that can be extracted from the timestamps of photon arrival sequences is given by the entropy rate of this Markov chain, which is 1/1 plus dp times binary entropy of P. A simple PPM scheme was proposed by Kochman and Vornel. In this scheme, they disregard the detector's recovery time, so D is 0, and the term PPM stands for pulse position modulation. In this scheme, time is partitioned in frames consisting of n bins. In this example, n is 8, and only frames with a single occupied bin, which we call them active frames, are kept. Such frames carry log n bits of information. So we let omega denote the random number of occupied bins in a frame. So the raw key rate of the simple PPM scheme is given as follows, which is 1/n, which is the length of a frame, times the probability of having an active frame times the probability, the number of bits generated from an active frame. In our work, we consider D to be non-zero, and we show that even for the simple PPM scheme, which is the simplest scheme that has been proposed for QKD, the raw key rate cannot be computed in the same straightforward manner. And for computing the probability of having an active frame, we cannot use the binomial distribution. Actually, we need to consider three different regimes for parameters n, which is the frame length, and d, which is the recovery time, and then use some non-trivial calculations to find this probability. And also, frames in this case are not independent, unlike the case d equals 0, so we cannot use the following equation. As for this equation, the frames need to be independent. And also, we show that if d is non-zero, and we use the simple PPM scheme for the case d equals 0, this scheme would be, it's not secure. Figure A shows the theoretical bound on the number of bits per bin that can be generated as a function of bin occupancy probability. As you can see, even for a small value d equals 5, the maximum achievable information rate is 60% lower than when d equals 0. And figure B shows the average fraction of active frames as a function of bin occupancy probability. And you can see that until the point 1/n, which is 4 times 10 to the minus 3, the average fraction of active frames for d equals 0 and d equals 400 are almost identical. Note that for the real experiments, the value of d is around 400. Also, we can see that after the 0.1/n, which equals to 4 times 10 to the minus 3, the average fraction of active frames tends to 0 as p increases. But for the case d equals 400, the average fraction of active frame tends to the value n over d, which is 0.64 in this example. Thank you.
All right. Any questions for Esmaeil? Okay, why don't you unshare your screen?